So happy birthday once again. And now to the main point of my talk. I'm going to tell you a story about what is in some sense, it's not the most fundamental quantum particle at all, but it has very important influence on human society and still expresses a number of the basic mysteries of quantum mechanics and shows some of the practical applications. I'm going to report to you work that's been done at the National Institute of Standards and Technology by the Neutron Interferometry group and show you how it connects with other areas of physics with which you may be more familiar. So the neutron is not quite a fundamental particle. In some senses, it's fundamental as a proton. We'll see more about that later. And it's certainly, I'm going to describe its quantum nature both as reflects the particle and its wave properties. I will show how those can be cast in ways that are now being studied with in the so-called structure waves of matter and light. You may know this field under the name of orbital angular momentum. I'll show you how that orbital angular momentum is imparted to neutron waves and show you some recent results in making a hologram using neutron radiation. Okay, so first, the neutron as a particle. Let's turn our eyes back about 85 years, to New Year's Day, 1932. So at dawn on New Year's Day of 1932, no one in the world knew anything about the neutron. There was a very different understanding of atomic and nuclear structure then. So for example, you're probably familiar that elements, a given element will often have isotopes. That is, an element has the same chemical properties, but they're different species with slightly different weights that differ by about a proton mass. And the origin of that phenomenon was completely unknown. The leading idea as to the origin was propounded by Lord Rutherford, or Sir Ernest Rutherford then. It turned out to be completely wrong, but it had an allure. And the idea was that for a given element, the nucleus might consist of different numbers of protons, but then there would be some very tightly bound electrons inside the nucleus that would each such electron would neutralize a proton, so that, for example, you might have a species of hydrogen which had a nucleus consisting of 2 protons and 1 tightly bound electron, so that the mass would be approximately 2 proton masses, but the charge would be 1 unit of proton charge. In fact, the discovery of that isotope was one of the holy grails of isotope physics in that day. It had never been seen in mass spectroscopy. And on New Year's Day, there was reported in the Physical Review the discovery of a hydrogen isotope of mass 2 by Harold Urey, Frederick Brickretta, and George Murphy. Again, it was a report of a discovery of such an isotope by use of atomic spectroscopy. But once again, there's no foundational idea as to what constituted it, except it was sort of the simplest possible isotope. So about 6 weeks later, Chadwick, about 1 day after a longer paper was sent to Physical Review by Urey, Brickretta, and Murphy, Chadwick mailed his account of the discovery of the neutron to Nature. And I'm showing you Chadwick's paper, Nature, in its entirety, not so you can read it, but just so the next time you start to complain about how your incremental advance is exceeding the 4-page limit of Physical Review letters, here's Chadwick, in a column and 1/3, charitably reporting this foundational discovery of the neutron. It was quickly realized that there was a neutral particle with about the mass of a proton. And I guess for me, one of the first and really visionary ideas about its origin was expressed by Heisenberg just a few months later. And it seems almost crazy because the neutron, so Heisenberg understood the neutron and the proton had the same mass. Well, one was neutral, one was charged. But he said, well, we should consider these to be two different levels of a two-state quantum system. It's like saying, one is charged, and so there should be an operator that connects them. Our usual, this is, something familiar to all of you, the sigma x operator, that there'd be some operator that changes a neutron to a proton. Well, changes a neutral object to a charged object. It's kind of like saying the cat and the dog are two states of a two-state quantum system. What sort of transformation takes a cat into a dog? But this concept instantly solved a wide range of problems because he said, furthermore, given this, then the anti-symmetrization principle, which we use to describe nuclear structure, should include both the space degrees of freedom, the spin degrees of freedom, and then this new degree of freedom, which is now called isospin. He didn't use that word. So then, in other words, in order to construct a first principles picture of nuclear structure, you have to take this Pauli, you have to treat the proton and the neutron as identical particles and perform the anti-symmetrization appropriately. So this gives, for example, going back to the deuteron, old Deuteronomy, it instantly tells you that the ground state of the deuteron has to have an angular momentum of at least 1 in units of the reduced Planck's constant, just by taking, and that was later verified. So this is actually a predecessor to the quark theory of matter. It's a higher level of the description, so it's still valid, but it opened the door to really understanding the quantum structure of nuclei in a quantitative way. In fact, for a while, here's an older periodic chart of the atoms. It shows the neutron as a member of the periodic table of the element in the same sequence as you can see the noble gases here. So it's an element with atomic number 0. Now that is no longer the common conception. It's recognized basically as an isotope of the proton, isobar of the proton, and there's not much chemical significance attributed to it. But there's another representation with which you might also be familiar, the chart of the radionuclide. So the predecessor here shows all the elements in the periodic table as they were known at some time in the past. This is a more current representation, the chart of the radionuclides from the International Atomic Energy Agency. It shows all the known nuclei, all the nuclei known in nature, subject to some proviso that they live for a time long enough to be observed. In this representation, which the neutron number is indexed by the whatever it is, the column, the x-coordinate, and then the atomic number, or the proton number, is in the vertical direction. And I don't know, maybe you can see it right here, down there, right there. There's this, well, it's like Singapore at the end of Asia, isn't it? This is sort of like Malaysia here. Not too bad, it hadn't occurred to me. And then there's this little tiny island of great power. Can someone suggest to me what the significance of hanging off the edge of this continent is? What gives something like that such amazing, but an exceptional power? Oh, I just have to put in a plug for this book, Discover the Isotopes, which literally tells the story of the discovery of each of the 3,000 radionuclides that's present in this array. Very, very interesting. Well, to get back to Malaysia and Singapore, of all these nuclides, the neutron is the only one that has no electric charge. All the others have positive charges. And so, if you recall your basic atomic physics, if you bring atoms together to form a molecule, you can only get them so close because eventually the positive charges of the nuclei repel each other. As you might remember, the further understanding of nuclear structure was made possible only by having high-energy nuclei to engage in collisions, because in order to get any two nuclei to merge, you have to give them energies of millions of electron volts to overcome this Coulomb repulsion barrier. And the neutron, on the other hand, being electrically neutral, can penetrate any nucleus without lever hindrance. So even at thermal energies, a neutron will go, as you'll see momentarily, will go right into any matter, whatever, and be completely unaffected by electricity, by electromagnetism. So this had an amazing consequence discovered soon after this remarkable experiment, also in the year 1932, which Cockcroft and Walton at the Cavendish Laboratory built an accelerator that could accelerate particles up to of the order of 1 million electron volts of energy. And they found that when they accelerated a proton and collided it with lithium, it produced 2 helium nuclei, or alpha particles, with an excess energy of 17 million electron volts. So in other words, they put in something with an energy of a fraction of 1 million electron volts and got 17 million electron volts out. It was astonishing. It's an incredible source of energy. And the press went wild, heralding a new form of energy far more powerful than anything had known. And Lord Rutherford, then Sir Ernest Rutherford, was quoted, sort of dampened the enthusiasm a bit. What he says here, actually in retrospect, is both prescient and also ignores a major point. So the short version of what he's saying is, we need to make these accelerators accelerate all these particles up these high energies. The cross sections are low. So it's ridiculous to think about this as a practical source of extracting energy from the nucleus. Now, of course, the whole fusion program, which I guess it hasn't actually worked yet, but I mean, everyone believes it could in some way. The sun works this way, but we don't have the sun on Earth yet. It is possible to have thermonuclear explosions and stuff like that are based on just this type of reaction, but it hasn't happened in a practical sense yet on this planet. Well, here's an amazing person, Leo Szilard, who gives an account of this epiphany he had when thinking about this discovery the discovery of a source of nuclear energy inside the nucleus. Walking down Southampton Road near the British Museum in London one day, he stopped for a stoplight, and he said, well, for the neutron, you don't need this high energy to cause the collision. So all we'd have to do to make a practical source of nuclear energy is find a system which would absorb a neutron and then emit more than one neutron, and that could be the basis of a chain reaction. So he didn't waste his time writing a letter to the editor of Nature in order to get all these tiresome comments from referees, he sat down and wrote a patent application, patenting this idea. Okay, who here has never read a patent once in their life? Hands up, everyone, because I know it's true. Some of you have actually read a patent? Come on. Oh, good. Thank you. Did you read it as well? Just kidding. So many of my colleagues say, I've never read a patent. Well, this is one well worth reading. It's only like 6 pages long. You can get it from the British Patent Office. So he did not know what element might be the source of you needed this mystery element that would absorb a neutron and emit more than one on average. He didn't know what it was, but he made some speculations in his patent application. The patent was granted 1936, and immediately it was assigned by Dr. Szilard to the Admiralty. It was kept secret for a while and then released in 1949. He was no one-trick pony. Here's another one. This is even a more beautiful, amazing patent by Szilard and Enrico Fermi, which is patenting a neutronic reactor, something that they actually made work. And here's a famous, juxtaposition. Here's Chadwick's paper, February 1932. In December 1942, not 11 years later, this thing that Chadwick reported, which was unknown previously, had no known applications, act of pure basic research, had been shown to realize the most powerful source of energy ever seen in this working nuclear reactor constructed by Enrico Fermi and his team at the University of Chicago. So let's see. 10th anniversary Center of Quantum Technologies. We're now working on year 11. I mean, okay, this is a pretty high bar, but why not have some stretch goals? Here's a picture of a working reactor at the University of Maryland. So nuclear reactions are now a source of lots of useful and interesting things. Here's an American aircraft carrier which has visited Singapore in recent times. It's powered by two nuclear reactors. Like, never take one nuclear reactor to sea, right? Take at least more than one. Each generating about 500,000 watts of thermal power. Any ex-naval personnel in the audience? So there's something about a nuclear reactor aboard a submarine or an aircraft carrier. And the main thing I'd like to point out is it's an incredibly powerful source of energy, and so it obviates the need to carry along fresh water, which for an aircraft carrier which has 5,000 people aboard it, fresh water is a critical element, also for the operation of the catapults. So basically, this ship carries, at any time, it carries about a 25-year supply of fresh water because it can evolve, and does evolve, 500,000 gallons of fresh water each day from desalination of seawater. You cannot do that with a fossil-fueled vessel. Let's say, I just mentioned for comparison, the typical nuclear power plant in the state of Washington, United States, operating at about 3.5 gigawatts thermal power. That's the conventional figure of merit that's used. Electrical generation is about 30% efficient in these plants. So this one reactor would support about a gigawatt of steady electrical power, which is about 1/6 of Singapore has a operating capacity of about 6 gigawatts. Okay, so now getting onto the wave aspect of neutrons, there's a very simple mnemonic that's often used by people who work in this field. The characteristics of the thermal neutron in terms of its speed, its velocity, speed, 2,000 meters per second, 2 kilometers per second, kinetic energy of 20 millielectron volts, which is just the thermal equivalent of room temperature. Do you agree, Christian? And then a corresponding de Broglie wavelength of 2 angstroms, or 0.2 nanometers. So the thermal neutron has a de Broglie wavelength that's very similar to the, similar in size to the spacings between atoms in bulk matter. So it makes it sort of an ideal probe of various properties. So let's talk about those, the wave properties of the neutron briefly. The work I'm going to, experimental work I'm going to show you has been accomplished at a research reactor on the campus of my employer, the National Institute of Standards and Technology. Here is the reactor building seen from the air, and then there's a guide hall for neutron experiments off to the side. There's some automobiles in the parking lot to give you. Yes, American cars are bigger, but some of these are made in foreign countries. So here is, I think, one of the most evocative portraits of the implications of the electrical neutrality of the neutron. You see here on your left a cell phone camera photograph of 2 flowers inside a lead cask. A lead cask is used to, safely transport radioactive materials from one place to another within a research laboratory. And here's exactly that same object seen from the side by neutron radiography. So in this case, there's a source of neutrons, a reactor, and then this cask containing flowers seen from the side. The neutrons pass through, and you can see the shadow image. And I'd like to point out that here you can see the vein inside a leaf of a flower inside a lead cask, and you can see the stamens and the pistils inside the fragile blossom of this flower inside a lead cask with neutron irradiation. See, this is this type of detail that you cannot see by other sources. When Superman was born, the neutrons weren't known, so he had this disability. His X-ray vision couldn't see through lead. He did not have neutron visions, which caused him, they say, troubles with his girlfriend. Okay, now, so that shows at least you can make shadow images with a neutron. What about the real thing? Wave interference. So here's, everyone from childhood has seen patterns like this in nature. Thomas Young, from those patterns, inferred that light was a wave. This is an illustration from his original paper. We call it the 2-slit experiment. It was actually done with pinholes in a card, and just like throwing 2 pebbles into a pond, he used the pinholes in the card, put filtered blue sunlight onto the holes, and observed the interference fringes on a remote screen. And maybe I wasn't actually aware of this until I read Young's paper, which you can get on Google Books. He not only measured the wavelength of the light from the interference pattern, so he said it's a wave. Well, a wave of what? It wasn't clear what the what was in the wave. But anyway, it could be a wave. Well, then a wave has a wavelength and a frequency. So he inferred the frequency of the oscillations of blue light. Whatever was oscillating, at least he used this, C equals lambda nu. Then you do some simple algebra, you get nu. And he inferred the frequency, which is for blue light, it's like 10 to the 15th hertz, something like that. Just an unimaginably large number compared to ordinary experience. And even in recent times, the direct measurement of frequency of light at those frequencies is it's a challenge that was recognized by the Nobel Prize in 2005. So then another aspect of interference, the Michelson interferometer, gave us the understanding experimental basis for the theory of relativity. And now, every time you pull out a telephone, right, and look at a cat video, somewhere on you're using an optical telecommunications network for which the high-speed switching capability is provided by Mach-Zehnder type interferometers. And the most sensitive measurement instrument ever devised, the Ligo, once again is based on the Michelson interferometer. Here's the schematic of the operation of Ligo as presented in the original paper published, well, I guess it's almost 2 years ago by now. No. Well, yeah, almost 2 years ago by now. And Albert Michelson, if he could see this, would say, well, it's just a straightforward implementation of my idea, using this interference to make all these precise measurements. Well, you know what's coming next. This is something that, most of us just glide past it. But when you, or at least for me, when you see it in practice, it still is a mystery. We have a very, simple to understand picture of waves. But when we get down into the quantum regime, we'll also deal with discrete detection events. These are really apparent in neutron interferometry because, sort of anticipating things I'll show later. The flux of neutrons in these experiments is very low. So you're literally collecting collecting data at such a rate that you can hear each click, or you can easily see in real time each click that develops in a neutron interferogram. The click signifying the detection of a neutron at a single point in space, or in a limited region on a position-sensitive detector. And by the way, for reasons I can't go into right now, those detection events are all completely destructive. Actually, I'll say a little bit more about that. The neutron being electrically neutral, thermal neutron, let's say, with thermal energy, being electrically neutral, cannot be accelerated to an energy sufficient to cause excitations in ordinary matter. So the only way that it is detected in practice is by using another isotope that absorbs a neutron which causes a fission reaction to generate energetic fragments. So helium-3, for example, is one such. A zero-energy neutron on helium-3 causes the destruction of the neutron and the helium-3 nucleus, the production of tritium and of a triton, or hydrogen isotope of mass 3, and a proton with an excess energy of about 3/4 million electron volts. So every neutron detection event is destructive. And it basically, we don't really see what goes on around the tree, but we do have, the clear evidence of the outcome in neutron interferometry. Now, this is a mature technique pioneered in Vienna by Bonza and particularly Helmut Rauch. It's still a major center for neutron interferometry. In fact, Anton Zeilinger, well known to all of you, was trained, got his basic training in practical quantum physics in neutron interferometry, working with Professor Rauch. Here is a recent second edition of a monograph on the subject, published by Oxford University Press, 2015. Kind of the iconic experiment in this field was the first observation of gravitationally induced quantum interference. So this is an amazing experiment in which a basic Mach-Zehnder interferometry looked at the interference fringes associated with a neutron, which was split into two paths, one of which went uphill in the gravitational field before the other did, and found that the action of gravity on a quantum particle was consistent with the very straightforward interpretation of it as being a scalar potential. But I mean, I'd say this is still an area where there's room for precision test, and the independence of gravity from all the other laws of physics is, I think, one of the outstanding, but the apparent independence, present independence of gravity from all other fundamental forces is still one of the great puzzles of physics. So here's a photograph of a working neutron interferometer. It's about the size of a soft drink can of Coca-Cola. Here's a ruler scale, a measurement. Basically, you have a neutron incident. It is exactly like an optical Mach-Zehnder interferometer. Neutron incident on a beam splitter. One path the neutron can take is just to go straight through the beam splitter. The other is to be Bragg reflected. So actually, in atom interferometry using Bragg pulses, you do very similar things. Then there's a second beam splitter here, which actually acts as a mirror. So the neutron on this path, a part of it will be transmitted through this blade and so lost to the interferometry process. But then another part is Bragg reflected. And then similarly, for this path, neutron here, part of it will be lost in interferometry, the other will be Bragg reflected. And then there's another beam splitter here, which recombines the amplitudes, if I can say it that way, the amplitudes associated with both paths, and puts one in the A plus B output channel and one in the A minus B. It's just a very straightforward Mach-Zehnder interferometer, though it's, I'll just hasten to add, technically demanding to implement in practice because you need the crystalline planes of each of these three blades to be more or less in exact registry. So this means you can't put this together from discrete components. You could never possibly align two crystals separated by of the order of 10 centimeters to within angstrom level accuracy. You need to start with an ultra pure silicon crystal and cut away the pieces that you don't want. And it gives the fringe contrast characteristic of, this is experimental data showing the output in these two Mach-Zehnder output ports as a function of the angle of a phase shifting element that's used to change the optical path difference, the effective difference between the two neutron paths. And from that, one can then, this is a technique that's been used to, for example, measure the scattering lengths of neutrons scattering by electrons and neutrons scattering by nuclei, long-standing. Okay, so now I'm going to turn briefly to quite a different field, which is passing under the name of structured waves of matter and light. And for example, just during this year, there have been a number of, this year heralds the 20th, everything's an anniversary these days. This year is also the 25th anniversary of a foundational paper published by Les Allen and others on so-called orbital angular momentum of light. This is the discovery of a way of taking a light. Well, I'll show you in more detail, but if you think of an ordinary plane wave, you can, where the wavefront just propagates as a plane, it's also easily possible in theory to imagine that the plane would be twisting as it propagates. And Allen et al. were in some sense the first to demonstrate this in a controlled way for light. And then there were follow-ons in matter waves, atoms, neutral atoms, electrons, and neutrons, and actually in a variety of other wave motions. So this is, there's two major review articles, or actually full journal issues published earlier this year on the so-called orbital angular momentum of light and matter. Here's one in the Philosophical Transactions of the Royal Society and another in the Journal of Optics. Provide very comprehensive survey of developments in the field. Well, now, what is the basic idea of orbital angular momentum? Let's just start with a Schrodinger equation for a free particle, and you know that it has these plane wave type solutions. These are the things that are used in all the standard treatments of scattering theory, starting from those of Lord Rayleigh, applied to sound waves in the late 19th century. And so the plane waves are sort of a complete set of waves that can be used to represent any type of wave motion that you like. There are alternative bases, and here's one in which you have a plane wave moving along one coordinate, x3, and then there is another independent motion in the plane of the wave front. So the standard plane wave can be represented by phase fronts that just propagate. This is the standard plane wave. Phase fronts that just propagate uniformly as they move along. So at any given moment, there's a plane of constant phase that's perpendicular to the propagation axis. But then one can also, at least mathematically, find quantized orbital motions. So there are waves where the phase will evolve through one cycle of rotation for each wavelength, or for two, or for three. And these are probably known to Maxwell. They were certainly known in the early 1930s, but then were only recently implemented in practice. Very beautiful experiment done in the Ukraine, 1990, which demonstrated this. There's another buzzword for you: screw dislocations in the wavefront. So in other words, there's a singular structure, or a screw twisting structure in the wavefront of light of this time. And it's beautiful. It's really a highly imaginative experiment. I just have to mention it. This group in the Ukraine had, once again, the workhorse of everything, like the foundation of quantum physics, the Mach-Zehnder interferometer, a laser beam shining on a beam splitter. There's a reference beam that passes through the beam splitter, and it's reflected off a mirror. It's expanded by a spherical lens, goes to a second beam splitter, and then the other beam, split down here, goes through an object that twists the wavefront of light, and then it comes through and on this beam splitter, and you see the output. In this channel, it shows the interferogram. I'll get back to that in a moment. This is a spatially resolved interferogram as seen by the group of Soskin and Alien. What is this object that they use to twist the light? You've done it yourself many times. Here it is, courtesy of the Barilla company. There's a form of wholesome wheat product. Spaghetti, I think it's called in Italy. These are stalks, straight stalks. And if you just put them down in a glass, they tend to splay out in a sort of spiral-looking pattern. You've seen this many times. Here's another famous example, this sculpture, Tractricious, which is an apparent spiral. Do you see the apparent spiral motion? But it's constructed of straight rays. Each of these, the members of the sculpture, is just a linear beam, just a linear trajectory. But they're spaced around it so they give the appearance of a spiral motion. Here's someone standing inside Tractricious, posting the results on Instagram, and you can see there's a spiral motion. And then earlier this year on Reddit, there's a Reddit big hit showing a moving version of that type of representation where you have let's say, a rectilinear trajectory, but when you rotate it around you see it goes through this curved hole, and so you imagine there's something moving along this line would be executing a spiral motion. Okay, so now this pole is held in place on a fixed base. There's no real mystery as to why it's executing the trajectory it does. But what is remarkable is to think that even when there's not such a mechanical supporting element, you could have the same thing happen. So once again, here's this interferogram that was seen with the twisted light. And for comparison, here is on your right here is the standard interferogram that you'd see if you just interfered a spherical beam with a plane wave without the twist. You get the famous Newton rings pattern. But now do you see this pattern here, in its periphery it's just the same as the Newton's rings pattern. But do you see that in fact here for the Newton's rings you have this infinite set of disconnected layers of phase. It's like a cake, wedding cake or something like that. But now there's basically one continuous band of black interleaved with one continuous band of white. They're broken at the center. So in other words, the entire topology of this interferogram is changed radically by the twisting of the light. So that has been done for light, for atoms, for electrons, and now I'll say for neutron waves, and accomplished by very, very simple technique that was first used for light and to some extent for electrons, so-called spiral phase plate. And the basic idea here is that the spiral phase plate, you have the quantum particle traversing the plate, say starting from below. So if you think about it in terms of interfering paths, the particle can come through a narrow part of the plate where the small quantity of material causes a small phase shift, and then depending on where it comes through, it gets a larger and larger phase shift as it goes around, and you arrange the spiral phase plate so that the difference in paths between the thinnest and the thickest part of the plate corresponds to a wavelength, a de Broglie wavelength, or a multiple of de Broglie wavelengths. So basically, here's a very nice review article by Alison Yao and Miles Padgett showing schematically how this happens for light. And we implemented that idea using common aluminum dowel stock, macroscopically machined. Oh, there's a lot of shopping malls in Singapore, I'm told, and you might conduct the study I'm about to report yourself in the shopping malls. Very easy. So I have found that most spiral staircases are quantized in integral multiples of Planck's constant, by which I mean this camera doesn't reveal it fully, but basically at the top entrance to this spiral staircase, which winds around a little bit above. When you enter the staircase, I'll say it this way. If you start below on the staircase and climb it, when you exit the staircase, off screen here, you're headed in the same direction as when you entered. This seems to be a common element in spiral staircases. And in the shopping malls, I'm told, there are these mechanical escalators that allow you to go between levels. Not the elevators, but these walkways. And if you go through several floors, you'll find that a similar, so you can do experiments on orbital angular momentum in the mall. I recommend it. This is actually kind of I won't say that this is a trivial finding, but I say that the fact that this thing works for neutrons using macroscopically machined optics, how should I say? If you'd asked an expert in optical design to devise an interference filter for neutrons, the expert would probably say, okay, tell me what's the operating wavelength. The operating wavelength is 2 angstroms. Okay. Could you please machine us an object that will provide a 2 angstrom phase shift between paths? Well, that's like the distance between atoms. And in optical design, the figure of merit for making any refractive optic or any type of effective optical device is that the figure of the optic has to be accurate to some fraction of the wavelength of operation. Otherwise, it doesn't work. Take a nice mirror, scuff it with sandpaper. No longer a good mirror. So how can you possibly machine an optic that will perform satisfactorily for a wavelength of a few angstroms? And the answer is that for neutrons, neutrons behave much like light in matter, as we saw from that flower picture. And how do neutrons, those flowers that we saw, the flowers were scattering the neutrons. What force of nature do the flowers use to scatter the neutrons to form the image? Anyone? Yes, but there are these, is it the electrical force or magnetic force of the hydrogen atom? It is hydrogen, yes. It's the strong interaction. You're actually seeing a map of the strong interaction on a macroscopic scale when you do these neutron experiments. Okay, there's a slight caveat. The neutron does have a magnetic moment, so you can also do experiments in which you map out the effects of magnetism on neutron motion. But in most cases, non-magnetic systems, you're simply seeing the effects of the strong interaction. And so this, they call it strong because it's strong up close, but far away it's very, very weak. And so the difference of the index of refraction of most materials for neutrons from the index of refraction of vacuum is a part in 10 is a part in a million. So in fact, this criterion of optical design that the figure must be in conformance with the wavelength of operation, well, that obviously applies for reflectors, right? It applies for refractors because the difference in the index of refraction of a refractive material from vacuum is of the order of 1. But here, because of this very, very small difference of index of refraction, basically we have a bulk effect of the optic, and so you get an amplification factor of 1 million. You can tolerate, you just need micron level precision of machining to make to make phase plates for neutrons. Here's the basic implementation of phase plate in a Mach-Zehnder interferometer. Phase plate in one arm interferes with the path in the other arm, and there's a 2D imaging detector. And then for different values of the winding constant, or the topological quantum number, we see an interferogram that has the structure that's consistent with the winding number. And then here's a sort of a fermionic wave plate just made for the hell of it. Instead of making a winding number of unity, which is necessary to make a single-valued wave function, make it half integral, and that then gives an interferogram. Well, I'll talk about the details of that later if anyone is interested. Very straightforward principle. The addition of angular momentum is possible with these systems. So we have here the interferogram for a spiral phase plate with a winding number of 1, shows a 1 plus cosine theta distribution. Another one for the winding number of 2, shows the 1 plus 2 cosine theta. And that's like the old demonstration. 1 plus 2, how many is 1 plus 2? 3. Here demonstrated literally by the same type of gimmick, just concatenating the two phase plates, we see that you get the additive effect of winding number, and it's independent of the relative orientation. Okay, so I'll conclude very quickly with a more recent demonstration of using a similar, just using these spiral phase plates in a so-called holographic, in the production of a neutron hologram, basically following the same the original idea of Leith and Upatniks, are similar anyway. Wavefront division holography, where you have an optical element that causes a linear phase shift of a reference beam, and then the object beam, which is a photographic positive. Here's the beautiful picture used by Leith and Upatniks in the early 1960s to make a hologram. And we did the same thing using, once again, the Mach-Zehnder interferometer with a prism, which is, once again, just a piece of quartz to give a linear phase shift of the reference beam, and then using a spiral phase plate in the object beam. And we see here's the resulting image. It's to be contrasted with the ideal image associated with a wavefront twist of 2, so-called forked dislocation image. So this ideal image, if I were to expand it and you looked far away from the center, it would look like an ordinary diffraction grating. So it's what you get if you take an ordinary diffraction grating, but then dislocate one of the elements and split it into 2 parts. And so the size of the split determines the orbital angular momentum that's put into the outcome. This paper was, what do they say at the APS? One of the top 10 physics newsmakers of last year. Ligo was usually number 1. It says, while the selections may be scientifically important, the main criterion is how much cover they generated. Once again, it's the Reddit community that elevated this to their attention. Okay, so just to recapitulate, I tried to give you some insight into the origin, the applications, the basic nature of the neutron, its particle, its wave characteristics, showed you how those match up in many ways with those of matter and light. But again, there's this very large difference. First, we're talking about things that are mediated by the strong interaction, which is just kind of like irrelevant to almost every other mode of quantum motion that we experience in the laboratory. But nevertheless, it can be used in a similar way to give outcomes that resemble those that are known in other wave motions. And looking towards the future, we see that we can see the same type of structured wavefront generation for neutrons as we have for light and other quantum particles. Some of the imaging elements can be made using macroscopic screening techniques, and further downstream, if we're able to effectively control the quantization of neutron orbital angular momentum, then it, at the very least, provides a new quantized degree of freedom for neutron-based quantum information processing protocols, and perhaps longer term, the outline of a general type of control of neutron phase fronts for application in scattering and the like. And with that, I'd be happy to conclude and see you at lunch.